What's up, guys? This is Mr. Carlson. We are on our last lesson of the week, 6.3 population proportions. We're now going to be taking everything that we've learned and sort of mixing it together. We're still going to be doing confidence intervals, of course, and we're going to go straight to Desmos pretty much on all of those examples. But it's going to be a little bit different, and I'm going to explain that difference. It's instead of using studentized or standardized, we're going to be using proportions, and that does change things. So we're going to go through the homework quiz, the 6.2 if you haven't completed it, and then the lesson 6.3. Homework quiz will be 5 questions, 20 minutes, because you're really just plugging stuff into Desmos. And once you're done, make sure you review your answers as much as possible and then send them to me. Then get started on 6.3. Print out the note packet if you need to get started on that. Okay? How do I calculate population proportions? And then how can I use basically confidence intervals and point estimates in relation to those? All right. So without further ado, let's get started. The probability of success in a single trial of a binomial experiment is P. Now, this is something we learned way back when, like around 4.2, like about 4 weeks ago, we learned this. Okay, so probability of success in a single trial of a binomial experiment is P. Now, the probability is a population proportion. This probability is a population proportion. Okay, the point estimate for P, the population proportion of success, is given by the proportion of success in a sample and is denoted by this. So actually, this is going to be P hat. That's what we call. It's called P hat. I just can't write the P hat on Google Slides. But this is going to be X all over N. Okay? This is what we call a sample proportion. Okay? We're going to be using this a lot. So the point estimate for P, the population proportion, is given by the proportion of success in a sample is denoted by this. So this is a sample proportion, and it's basically going to act as if it's our point estimate, just like in 6.1, okay? Where X is the number of successes, where S is the number of successes, sorry, I'm moving myself up there, and N is the number in the sample, of course, the sample size. The point estimate, though, for the proportion of failures is Q equals 1 minus B, and that's just your complement. So if you succeed this much, the failures is just the 1 minus that. And then the symbols P and Q are read as P hat and Q hat. Okay? Perfect. Let's erase this, and then let's get started on some of these examples. So in a survey of 1,000 U.S. teens, 372 said that they own smartphones. Find the point estimate for the population proportion. Okay, so that means my N right here is 1,000, and then my X is 372. So that means my P hat, my sample proportion here is going to be 372 all over 1,000. And this equals 0.372. Okay? Not too bad, right? And again, so right here, survey of 2,462 U.S. teachers, 123 said that all or almost of all of the information they find using search engines online is accurate or trustworthy. Okay, so given the same sort of setup, my N is 2,462. That's sort of my quasi population of those people, of that population. The data that I'm looking at is 123. So I take 123 divided by 2,462. And this gives me roughly around 0.0499 So it's about 5%. I mean, you can just say that 0.05. It's about 5%. So this is basically your point estimate for the population parameter. Okay, so it's very similar to the point estimate of the sample when we found the sample mean and we used it to do work on the population parameter from 6.1. And the same thing here. That's what we're doing. Okay, so confidence intervals, the population proportions, what are they and how can I do them? Okay, so the definition, constructing a confidence interval for a population proportion is similar to just constructing a confidence interval with a z distribution or a population mean or whatever, and that's just section 6.1. You start with the point estimate and then you calculate the margin of error. You then have a C confidence interval for the population proportion is this data. So what I have here is going to be my p hat now, instead of my x bar, my p hat minus my margin of error, and then my p hat plus my margin of error. So very, very similar, right? This is going to be my left endpoint, and this would be my right endpoint. Okay? Makes sense? So very similar indeed, and if we were in class, we would actually do a whole activity on this, and it would be really, really fun, but unfortunately, it's that day. Okay, so as you can probably tell, it's going to be very, very similar. So think about this. My E now, what is going to be my E? My E is slightly different. We're still going to be utilizing my z-score or my z critical value, but I'm going to be having a different E value. And this is going to be my P hat times my Q hat all over my N. This is actually my margin of error, and it is rather nasty. We're not going to solve these by hand at all. We're going to go straight to Desmos and just solve it all using the calculator. However, still, it's pretty nasty. Okay, just letting you know. The probability that the confidence interval contains P is your C, so basically whatever C value that is, that's 90% or 90%, 95%, 99%. Assuming that the estimation process is repeated a large number of times, of course. Okay. Now, a binomial distribution can also be approximated by the normal distribution, something that we sort of already figured out previously in the last couple of weeks, about 4 weeks ago. If n times p is greater than 5 and n times q hat is, n times p is greater than 5, and n times q hat is greater than 5. Okay, what this means is when n times p hat here, now this would be p hat, and on your notes, if you're following along, you see a hat there. Sorry, I just can't put it on Google Slides. Is greater than 5, and n times q hat is greater than 5. The sampling distribution for p is approximately normal with the mean of this. A mean of my mu, and then sub p hat equals p. Okay? So that means essentially my population proportion is going to be equal to my actual population mean, with a standard error or deviation of my sigma of sigma sub p hat, and then equals, I have p times q all over times q all over n. So a lot of these new formulas, I get that. And so we're going to just go through them like normal. We're going to verify that we can use a normal distribution and so forth. And the last thing that I need to show you guys is just identifying the actual sample statistics. Okay, so let's go through this, and then we'll get through some examples. Here are the guidelines. How can I create population proportions? First, identify the sample statistics n and x bar, okay, or specifically just x, whatever they are. What is n and what is x? You want to find the point estimate. This is p hat, and this is, again, just p hat equals, and then x all over n. Okay, verify that the sampling distribution of p hat can be approximated by a normal distribution. That is 2 tests. So I take n times p hat, and if this is greater than 5, then I'm good. And I also take n times q hat, and if that's greater than 5, then I'm good. Both of these need to check out. If they do check out, then you can do a normal distribution on this proportion. All right? If they don't check out, you're not going anywhere. So it's a little bit different than the other two. And then find the critical value, my z-scores back again. and we're going to use Desmos to find those critical values. So I'll kind of slightly go back and forth between Desmos there. Okay? And then lastly, we will have to find the margin of error, and then we will have to find the endpoints. So once again, my margin of error is this big monstrosity, my z-score or my critical value times the square root of my p hat times my q hat, and then all over my n. Don't worry, we're not going to be solving that out by hand. And then my left endpoint would be just my p hat minus my e. My right endpoint would be my p hat plus my e. And then my interval would be my p hat minus my e, and with my population proportion in between that and my p hat plus my e. Okay, so very, very similar indeed, just a couple things that we need to kind of square away, specifically if we want to verify it's actually normally distributed, and my e is a little bit different and so forth. But again, I'm going to be utilizing Desmos a lot. So let's erase this and let's just get right into it. So use the data from example 1.1 to construct a 95% confidence interval for the population proportion. So what is this? So that means let's list out our data first. Well, I said my p hat was 0.372, which means my q hat, something I haven't found yet, is 1 minus that. So what that equals is 0.628. Okay? And then my n we said was 1,000. All right? I want to verify that this is a normal distribution. So that's my second thing. I want to verify that this is a normal distribution. So how can I do this? Well, I need to do two tests. So my first test is I need to take n times my p hat. And don't worry, we're not going to be doing this every single time because it is rather tedious. In fact, you'll probably never ever do this. But I do need to show it to you because it's the math, right? So I take 1,000 because that's my n times my p hat, which is 0.372. And this is actually going to be 372. This is definitely greater than or equal to 5, so it checks out. The second thing I need to do is my q as well. So my n times my q hat, and then equals. My n is 1,000, and then my q hat is 0.628. So when I multiply that, I actually get 628. That's definitely greater than or equal to 5. So again, it checks out. So it does verify, which means I can actually start solving this. I do want a 95. My C level is a 0.95. This is a 95% confidence level. Okay, so that means I need to find a z-score of that confidence level. So my z sub c will be 1.96. How do I do that? Let's find out. I'm actually now going to go to Desmos and do everything else so that we can get my interval. I'll even show you what the margin of error is, so you can write it down and get it, but I'm going to just show you my interval, okay? All right, let's get started on that. I don't want this. Let's go over here. It's going to take a minute to load. Wow. Give me 1 second, guys. Okay, so this is my 6.3 calculator. Very, very similar, right? Very, very similar indeed. Nothing's really changing too much with that. Okay, so this is my 6.3 calculator. I do need to change these values, so that's 95, good deal. And then I go down, and that is how I find my Z critical value. So that's how I find my Z critical value. Exact same thing as it was before. Yeah, it's the exact same thing as it was before, guys. So nothing's changing there. Now the point estimates. This is when I have to actually adjust my values here. So what's my P and what's my Q? Well, I had to first put in my X and my N. So actually, let's erase this. My X in this case was 372. And then my N here was 1,000, if you remember correctly. 1,000. And so now you actually see that this calculates it for you. So we are no longer going to need to calculate this by hand, guys, because it calculates it for you. All right. And then it also calculates your margin of error. So whenever it asks you for your margin of error, then just make sure that that's what it is, because that's what you need to know. Okay. And then I'm going to go over here and actually just calculate my my interval. I'm going to swoop this over, and this is my interval, and it already calculates it. So that's awesome, right? This is my interval. So 0.34 comma and then 0.40. So this is my population proportion interval. Not bad, right? Not bad at all. And so for now on, we're now going to skip this verification process because we don't really necessarily need to verify, and I'm going to just drop it all together because most of them will be normally distributed. And so I just wanted to show that to you just in case. Very rarely will you see that's not normally distributed, okay? So let's move on to our next example, and let's just start hashing these out, okay? Use the data from example 1.2, construct a 90% confidence interval. So what was the data from 1.2? Well, first of all, from 1.2, my p hat was 0.05, okay? Because if you remember, my n was 2,462, whereas my x, if you remember, was 123, okay? I do want to find a 90% confidence interval, so that's what my C level is. And then we literally just start. This is all the information we need to know, guys, because guess what? We just start going to town. Like, we just literally plug it all in. That's all I need to know, and then everything else will take care of it. That's amazing, right? So I just do 0. I go down. Okay, that's my critical value. If I want that, if it asks for that, I go and change my X and my N here. So my X is going to be 123. My N, whoops, let's go up and erase that 1 3 there. And then my N is 2,462. So notice how I get the same P and the same Q for my probability of success and so forth. Pretty cool, right? Yeah? Pretty awesome. Okay. And then X, actually, let's scroll down. This is my confidence. Sorry, this is my this is my margin of error right here. So pretty nice. It's my margin of error. And then this is what my actual intervals are. So I have from 0 to 0.43 roughly. So my interval. As I write it down, I have from 0 to 0.043, and I have 0.057. That is my confidence interval for my population proportion. So right here, those two. And guys, that's literally it. There's nothing more that you need to do. So as you can tell, can these go really fast? Yes, these go extremely freaking fast. Okay, so let's actually go to town on these. Okay, so this next one, a figure is shown from a survey, uh, um, survey of 498 U.S. adults construct a 99% confidence interval. So let's figure this out, okay? So first things first, I want to label all my stuff. So they actually give me the p-value here, which is kind of unfortunate because we don't have an x value. So this one we actually do need to solve by hand, unfortunately, because they don't give us a p-value. We don't have an x. Although we could probably find the x value, and actually let's just do that so I don't need to go through all the headache. So let's just find the x value here. But before I do any of that, my n is going to be 498. Okay, my p hat, they do tell me my p hat is I want to know the teenagers, about the teenagers, and they give me, this is the probability of success. So it's actually 0.71. Okay, my c value is 0.99 because we want to know the 99%. We want to construct a 99% confidence interval. And then we will go as follows. Now watch. If I use my p-hat formula for x all over n, I don't know what x is. It doesn't matter. In order to use this calculator, and without calculating everything else by hand, what I can do is this. I can type in 0.71 for my p-hat equals x all over my n, which is 498. So now what I can do is multiply 498 to both sides, and then I can get x equals. It's a rather intuitive way to solve it, really, and it's really great. So I'm going to type in 498, so 498, and then times 0.71, and this gives me 353.58, okay? 353.58. Now, you can round, of course. It doesn't really matter how you round this to be. I'll probably round up, so I'll probably just make it equals 354. So I'll probably say x equals 354. Let's do that. So now that I know my x, now that I know my n, now that I know my everything else, I mean, that's really all I need to know, my n, my x, and I need to know my confidence level. Once I know all that, I can then go back to Desmos and start typing this stuff in. So that's 99. I don't need to change anything right here. Let's scroll down. I do know my n at the very beginning. What they told us, it's 498. And then right here, I'm going to say 354. Okay. So now notice my p is the exact same, right? It's 0.5 or 0.71, which means it tells me my e, and it also tells me my confidence interval. So I didn't even need to go through it by hand. You could solve it completely by hand, but if you didn't, or if you're not given that x value, you would have to find it. Okay, which is again really, really unfortunate, but something that we need to do. What's my interval? Now that I use my calculator and it just solved it all for me, my interval is 0.659, comma, and then 0.763. This is my final answer. That is my final answer. That's my confidence interval. That's what I'm trying to find. Okay? I hope that made sense. I hope. Okay, so let's erase and let's knock down the next question. We're going to use the same kind of data, but now we're going to construct a 99% confidence interval, but not with teenagers, but with people over 65. So now I'm going to use 0.25. So my C level is 0.99. My N is still going to be 498. But now what's my X? So if my p hat is 0.25, what I'm going to then use is 0.25 equals my x all over 498. I solve that real quick. I just multiply 498 to both sides. So I'm going to have 0.25 and then times 498. And then I get 124.5, and I'm going to round that up to 125. So that means my x is 125. So that is not my actual answer. Okay, that's just my x, but I need these three in order to solve for my population proportion. So I go back to my calculator, and I'm pretty sure it's already at 99. Yep. So it's already at 99. So now I need to change my x value here. That's the only thing I need to change, and this is going to be 125. Okay? That's going to be 125. Now notice my p hat is roughly 25, just like what they've been given, my population proportion. That's my probability of success, rather, is 25%. So that's what it is, okay? And I scroll down and I notice that that's my margin of error, and this right here is my left and right endpoints. So roughly 0.2, so my interval, my actual final answer here, my population proportion interval is roughly 0.2 and then 0.3. That's my final answer, my interval. Awesome, right? Awesome, awesome. So now we are almost done. That's all the confidence interval things that I have to go through. It's very, very simple. It's probably the easiest out of all of them, to be honest, after you kind of use Desmos just over and over and over again. I'm going to go through one more topic that I want to get through, and that's finding the minimum sample size, finding the minimum sample size. And this is probably going to be completely by hand. So let's erase this. But that's the bulk. The bulk is the actual confidence intervals. So how do I find a minimum sample size by hand? It's going to be using this formula. So given a C confidence level and a margin of error, the minimum sample size n needed to estimate that p hat value, this p hat value, is going to be n equals my p hat times my q hat, and then times my z-score critical value all over my margin of error, and then to top it all off, it's squared. So this is rather obnoxious. I mean, obviously it's really, really obnoxious, but that's okay. We are going to solve it by hand, but we have Desmos with us right here as a normal calculator. So I'm going to utilize that. Okay, awesome. So that's what n equals. And so assume, this formula assumes that you have a preliminary estimate. So maybe you don't have an estimate, right? Maybe if you don't have an estimate for your p hat or your q hat. If you don't, then you're just going to use 0.5 for both. Okay, if you do, you're going to be using what they tell you to use. All right, so let's actually erase this. And this is going to be our last example for this week. You're running a political campaign and wish to estimate with 95% confidence the proportion of registered voters who will vote for your candidate. Your estimate must be accurate within 3%. So that's actually my margin of error there. That's what they're telling me. Find the minimum sample size from 1. No preliminary estimate is available. So we're going to stop there, and we're going to get to 2 in a little bit. So if there's no preliminary estimate available, that means I'm going to use 0.5 for both my Q hat and my P hat. I'm going to use 0.5 for both my Q hat and my P hat here. Okay. And then my Z-score, my critical value. What is that? Well, if I type in for my critical value of my confidence level of 95, I should get 1.16. How do I do that again? I'm just going to show you. If I type in right here and 0.95, look at my Z-score, my critical value, my ZP is my Z-score critical value. I get 1.95, but it rounds to 1.96. So just showing you that just in case, but that's something that we should know or at least be familiar with. Okay, and my Z is that, and my C level is 95. Okay. My E, one last thing, is 0.03, and that is given to us right there. So let's type this in. I'm going to say N equals all of this monstrosity, following my formula. So are you ready? follow your formula that you wrote down. I'm going to first type in my p-value, so 0.5, and then my q-value, so 0.5, right? Perfect. And then I'm going to type in my z-score value, so at the top, 1.96. And then on the bottom, I have my E, which is 0.03. I'm going to end parentheses on that, and I'm going to square it, okay? And so that will become my minimum sample size. And I'm actually going to round that up to 1068, okay? Because again, I want at least this to make sure I cover all that is necessary. So my minimum sample size is going to be 1068. That is how many registered voters I need. Okay, that's how many registered voters I need. For my second one, what if the preliminary estimate is as follows, with my p hat being 0.31. So that means a lot of stuff actually does change. So if 0.31 is my p hat, that means my q hat is going to be the complement of that, and that means it's going to be 0.69. That's my q hat. But nothing else changes. My z-score is still 1.96. My C level is still 0.95. And then my E is still 0.03, right? So then what is my N? Let's plug all this in, and let's use my q hat as a 0.31, and my q hat as 0.69, and my p hat as 0.31. And then everything else is going to change or stay the same. Sorry, everything else is going to stay the same. Only these things are changing. So my q hat, or sorry, my p hat 31. Sorry, geez, the p hat's been a long night. And then my q hat 69. Okay, and so it's going to change to that, which means I still need to round up because I need to account for all that is given. So since I need to account for all that is given, I need to round up. So this is 914, okay? 914 registered voters is needed as a sample. Okay, so that was a lot of information this week. I understand that, guys. I'm going to erase this, and so we can get to the summary. But you guys have been great sticking with me. So find a point estimate for a population mean. That's what we learned how to find. We also learned how to construct and interpret confidence intervals for a population proportion, and also determine the minimum sample size required when estimating a population proportion. Guys, make good choices when doing the homework. Again, we're not doing a project here, obviously, but that's okay. Just do your homework and make good choices. Thanks for sticking with me. This is Mr. Carlson, C Squared Mathematics. See ya.